Hi there, and welcome back. What we're going to do in this video is take a look at antiderivatives, which is the reverse process of derivatives. And in order to understand how to find antiderivatives, we need to have a working understanding of derivatives. So as you see here, we notice that we have the derivative of x squared, which we know is 2x, and the derivative of x to the third, which we know is 3x squared. So we need to have a similar notation or a similar kind of relationship to show that we're starting at 2x and ending up at x squared. So that notation happens to be the integral sign that you might remember from definite integrals. So already you're seeing there might be a connection here. So this is an indefinite integral because there is no starting x value or ending x value. So the way this is written, the correspondence, is the antiderivative of 2x dx is equal to, well, what function did you start with? You started with x squared, but remember, we're basically answering the question, the derivative of what is 2x? X squared is not the whole story, but it's most of the story. Remember that you can also add any constant you want to x squared, and its derivative will still be 2x. So we write x squared plus c. And what that is, it really is a family of solutions rather than just one solution. You know, x squared plus 4 would have worked, x squared minus 1, x squared plus 8. All of those have derivative equal to 2x. So the most general of forms is just to write x squared plus a constant. So then for 3x squared, as you can probably gather, we would write antiderivative of 3x squared dx is equal to x to the third plus a constant. Okay, so here's the question. What if I just had a power function without a coefficient? What is the antiderivative there? So let's look at a couple patterns here. We have the antiderivative, let's do x to the fourth. Now, from what we know about derivatives, I'm basically asking the question, what do I differentiate to end up with x to the fourth? Well, let's see. If it's a power function, I know when I bring the power down, I subtract 1 from the power. So I know that that had to start with an x to the fifth and a plus c. But that's not the story, because the derivative of x to the fifth is 5x to the fourth. So the question is, what do I need to multiply that by to make that 5 go away? And that number is 1/5. If you take the derivative of 1/5 x to the fifth, you get 5 times 1/5 times x to the fourth, which is 1 x to the fourth. There it is, okay? So that means that this is our first antiderivative that we're guessing here. So if we wanted, say, x to the 13th dx, well, again, I know that my power had to start at a 14. And what do I need to multiply by x to the 14th to make the 14 go away? Because remember, the derivative of x to the 14th is 14x to the 13th. You might have guessed it. I need to multiply by 1 over 14. So there's our next correspondence. Okay, so it seems as though the antiderivative of x to the n dx is equal to, well, let's just trace out what's happening here. When the power in the integrand was 4, the result ended up being 1/5 x to the fifth. When it was x to the 13th, we got 1/14 x to the 14th. So it seems as though we are adding 1 to the power and putting that in the denominator as the coefficient, and then times x to the same power, the n plus 1, and then a constant. Now you can write that in a shorter form, x to the n plus 1 over n plus 1. Shorter, and it takes up less room anyway. So those are both acceptable forms. However, there's a problem. Notice in the denominator we have an n plus 1, which means this rule is not valid if n is -1. So you have to write a caveat that n is not equal to -1. So then the question is, how do we handle n equals -1? We handle it separately. So if n is equal to -1, we have the antiderivative of x to the -1 dx. Now that -1 is not doing me any good as a power that way, so I'm going to rewrite this as 1 over x, the more familiar way. And now maybe if you rifle through your derivative rules, there's a derivative that you learned whose result is 1 over x. The derivative of some function is 1 over x. And it turns out that function is the natural log of x. So great. Does that mean that the antiderivative of 1 over x dx is equal to the natural log of x plus c? Well, not exactly. Turns out, and this is a rule when we're trying to find any antiderivative, same kind of rule that tells us we have to add the plus c, we want the most general answer possible. So it turns out there is a better generalization of this antiderivative that is leaving it at natural log of x. So let me explain. Let's look at the function natural log of absolute value of x, which is equal to the natural log of just x if x is positive. Remember the definition of absolute value. Absolute value of x is equal to itself if x is positive, and its opposite, its additive inverse, if x is negative. So we already know the derivative of natural log of x is 1 over x. Okay, so the derivative of natural log of absolute value of x is equal to 1 over x if x is greater than 0. So what is it if x is less than 0? Well, let's see. The derivative of natural log of negative x is 1 over negative x times the derivative of negative x. And you notice those negatives drop out, and we get 1 over x. So that means that both pieces have the same derivative, which means we can form one function that's defined for x not equal to 0 as opposed to just x greater than 0. So that means in our antiderivative up here, I'm going to add the absolute value bars. Now, why is that so important? Well, if you look at the integrand, which is 1 over x, its domain is everything except for 0, all real values of x except 0. So it stands to reason that our antiderivative formula should have the same domain, or at least a similar domain. We don't want to take half of it away. So at least with the absolute value, we're able to consider negative values of x as well as positive values of x. So in summary, here are our two formulas that we just talked about. Antiderivative of x to the n dx is 1 over n plus 1 times x to the n plus 1 plus c. And then the antiderivative of 1 over x dx is the natural log of the absolute value of x plus c. These are the first of many, many, many antiderivative formulas that you will learn as you go through this unit. It'll be a fun journey.